For my first sketch model, I decided to imitate a stingray's movement in its navigation in the water. A stingray utilizes the lateral line system that detects movements and pressure changes in surrounding water. As you can see here, there's an abundance of sensors near its head as opposed to near its tail. According to these sensors, the stingray moves its pectoral fins in opposite directions, which aids in its movement in the water. The fins are moved by the muscle contractions that are notified in response to the pressure change. According to the frontal sensors, the stingray lifts its fins upward, gathering water underneath, then expels the water, which displaces its location from its initial standing. The low pressure on the front and the high pressure in the back pushes the ray forward. This movement is categorized as an undulatory gait, a wave-like motion that propels an animal forward. The uncertainties that continue to dwell consist of unknown buoyancy, as this movement is in water, as well as a created force that will move along the body of the stingray to replicate the wave-like motion. For my second sketch model, I have the ring-tailed lemur. Extremely long legs with significantly small arms limit their capabilities to walk on all fours, which prompt movement by jumping. Because their movement on the ground is difficult to recreate considering their unpredictability regarding the steps they take, I've decided to analyze and imitate how they jump from tree to tree. Lemurs jump from tree to tree by following a process, a series of steps that utilize their hind legs considerably. See how long their legs are. Lemurs' hind legs act as the driving forces which designate how much energy can be expelled. Takeoff begins sideways from their line of flight. They are essentially jumping backwards from their location. Lemurs then rotate their bodies in midair. Their hind legs, having kicked off, then swing forward as they act as shock absorbers once they make contact. Similar to their jumps on the ground, lemurs fully extend their legs to the highest capability as displayed here, which allows them to use more energy in traveling further distances. They have pads on their hands and feet, which allow them to stick to the surface they make contact with. The difficulty within this imitation is finding materials that work together in simultaneously extending and rotating in midair. And elasticity within the leg must also follow so that an accurate depiction of the extension is displayed. For my final sketch model, I decided to imitate the movement of E. coli. The flagella of the bacteria continuously rotate in a counterclockwise direction while also simulating a wave-like motion that propels it forward. The molecular mechanism within flagella consists of dyneins that are arranged regularly along the scaffold. A switch inhibition mechanism is present which designates one side to be inhibited and the other one active. By periodically switching the sides from active to inhibited, the flagellum alternates the direction of bending. In addition to this wave-like motion, the flagella also rotates about an axis counterclockwise. When the flagella rotates counterclockwise, the bacteria runs in a single direction. The problems encountered is that there are many mechanisms that need to be taken into consideration, considering the switching of dyneins as well as replicating an item that is continuously rotating counterclockwise and moving up and down in a fluid.